Okay. Maybe it's a little faster. It's not sure in the morning. Ishana somehow developed a lot of face swelling in the morning. I don't know why. I initially thought of postponing the talk today. Yeah, I got up. I don't know. Some missiles are floating around in the city. Mumps. Yeah, so this is the first talk of the session that I'm going to talk about randomized polynomial time identity testing for non-commutative circuits. This is joint work with Arvind and Raja. There is also a follow-up work of this result that we also do with Pushkar. He is not here. So I'm mostly focusing on the first result, and this follow-up results you can see in the archive. So yeah, so this talk will be a little bit different than the earlier talks in the sense that I'll be talking for non-commutative computations. So far all the talks I think that you have heard in the workshop are all over commutative rings. You take polynomials whose variables commutes. So in particular, let's be a little more formal and let's look at the algebraic object that we are interested. So this algebraic object is a non-commutative ring over n variables, and f is any field. So what do I mean by this non-commutative polynomial rings? It is just like scalar combination of formal words over z1 to zn. In particular, zi zj minus zj zi is non-zero in that ring for all I not equal to j. Right? For the commutative ring, these relations trivially 0, and that's the difference with the standard commutative computation, that variables do not commute, but the field is a standard field. So when you write a polynomial here, what you simply mean that it's a scalar combination of some words. So this wi's are words over z1 to z. And the degree of the polynomial is naturally the maximum length of a word that occurring in the polynomial. Okay. So yeah, so there is one line in mathematics or like non-commutative ring theory where people try to study the properties of such polynomials, and in particular they try to answer, like, given a polynomial f, let's say of degree d. Okay, one thing I must mention is that if you want to evaluate this polynomial, it is not very useful to evaluate this polynomial over fields, because then you don't exploit this non-commutative structure. It just becomes like a commutative computation. So to get anything meaningful about this polynomial, you must evaluate this polynomial over matrices that could give you some meaningful information. In particular, in this area of mathematics that called PI theory, people looks at following type of question. I give you a polynomial in the non-commutative ring over n variable and degree d, and you may like to know, like, what is the minimum K such that F is not an identity for the matrix algebra, let us say MKF. So MKF is a set of all K cross K matrices. This is like a typical question that people would like to understand in this line of mathematics.
F equals 0.
Yeah, so let me just define. What I mean by identity, F is a PI for MKF, that means for all tuple you evaluate the polynomial on any point on that matrix algebra, it will give you to 0. This 0 is basically a 0 matrix. That is what I mean by PI for the ring. Okay, so this is like a broad question that people study in this area, and there is a celebrated result by polynomial identities, yeah, by Amit Sur and Levetsky. It's 1950. The result is a very old theorem, and this theorem is considered to be one of the very important theorem in the subject. These people were working that time in Hebrew University, Jerusalem, and they came up with the following theorem. Let F be any field and let small f be a polynomial in this ring of degree, let us say, bounded by 2d minus 1. Then f cannot be PI for, let us say. So what they really proved is that take any field f and take a n-variate non-commutative polynomial whose degree, let us say, is as more 2d minus 1. The 2d, because there is a half difference, you can see from here that I want to write it like nice form like 2d minus 1. Then it cannot be the case that you plug this variable z1 to zn for every matrices on that d cross d matrices over the field F, you always see 0. It cannot happen. So this is what they proved in 1950. So notice one thing is that if the dimension of the matrix that you are looking at, where the polynomial is non-vanishing, is roughly like linear in the degree. Is the statement is clear?
This might happen for 2D, and so it could happen or it's a
Sorry?
tight, right? I mean, you
This is tight, yeah, this is tight, yeah. And they also gave an example of a polynomial which is like vanishing, these bounds are tight. Yes, you can of course have an identity in 2D. If there is a polynomial of identity degree 2D which will vanish on this.
so this is an example for the.
This is an algebra. Yeah.
I mean, this is an example, right? This is an identity for dimension 1 matrices.
No, he is asking for I think every D. Probably you are asking. Yeah. Okay. So that's polynomial called central polynomial. Okay. So now this the result of main result of this work gives you the following theorem. Let this work.
So if you want to
Yeah.
check with the 0, you have to start at least 2D plus 1 onwards.
If the degree is at least like bounded by 2D minus 1, you substitute matrices like D cross D. I'll come to that point. What do you mean by identity testing? I'm just defining, it's just a theorem in the ring. I haven't defined what is the consequence of it in the algorithm. That I haven't told you. So this work, what we prove is that let F be any field of size say greater than equal to. This is not a very serious restriction that you will see in the proof. I mean, in fact, you can do little better, but just for the sake of clean writing, maybe you will prefer to write that. Let So let's look at the statement. So choose a field which is like not a very small field, but not too large also, only like n times d. And let's say you have a polynomial f which degree is d, and the number of non-zero terms or non-zero monomials in the polynomial is t. Then what we proved is that this polynomial cannot be an identity for this ring mkf, where k is like logarithmic in t. So notice like many difference with the theorem of Amitzur-Lebesky. First of all, the dimension is not a function of d, it's not a function of degree. And the new parameter that it involves is the sparsity of the polynomial, that is the number of non-zero terms. So you can see the comparison between these two theorems. Almost, because the central polynomial is a example where number of monomials and its matches, because that is like standard polynomial that almost like you cannot improve it much. So that if you take this, yeah, maybe like one difference, I don't know. So S2n is an example where you cannot improve it much. It's like the S2n is this polynomial. N factorial. So that will be roughly like this. Yeah, I haven't talked much about this yet. So this is called standard polynomial. So yeah, I'll just come to that. I'm just giving you the main statement of the theorem. Okay, so to see the what it brings, let's take the following situation where the degree of the polynomial, let's say, is exponential in the number of variables in the theorem of Amitzur and Lebesky. That means the minimum dimension of algebra that you will look for any designing algorithm, that will be like exponential in the size of n. But here you could allow like exponential degree polynomial, but as long as the parameter t is also bounded by exponential, this is only a polynomial dimension, log of t. For example, you can allow in this theorem t to be something like 2 power n and d also like 2 power n. Still you get that dimension k is only like polynomial. Whereas this theorem, you cannot allow D to be 2 power n, then you have to consider very big dimensional matrices, which is not efficient for algorithm purpose. Yeah. To make that algorithm issue explicit, let me just give some CS motivation of this work. Is any question on the statement of the theorem? This is independent of any algorithm or any computer science result. It's just a theorem in rings, non-commutative rings you can think of. Okay, so no, only one proof. Its field doesn't matter. Yeah. Only you just minimal size should be there so that you can finally plug some interesting point from the field. That's all. In fact, Amitsur-Levesky theorem proof is also field independent. Field doesn't matter there.
The proof is what I'm saying.
Even the original proof is also field independent. So field doesn't matter in the proof. So let's see an algorithmic motivation. So we have seen what is a PIT problem in many talks so far. And PIT problem, you are given an arithmetic circuits and you want to test whether the circuit computes a polynomial identically 0 or not. The same question you can ask in the non-commutative domain also. In fact, in the next talk also will be on this subject. So by non-commutative circuit, I mean it's just like a standard arithmetic circuits with gates like, I don't need to define it now, multiplication and addition. Only thing that the product gate respects the order of multiplication. It doesn't mix that left and right. And question is the same given a non-commutative circuit C, does C compute an identically 0 polynomial? This is a question that you typically ask. Again, this brute force way of opening the whole circuit doesn't work, just you face the same difficulty. Okay. So what you do for identity testing of such a circuit? You have to really, these are the variables of the circuits. What you have to really do, you have to substitute this variable by some matrices and check whether the output of the circuit is a 0 matrix or non-zero matrix, and depending on that you have to decide. This theorem of Amitsur-Levesky gives you a direct algorithm to solve this problem in randomized polynomial time. So that result is usually given, attributed to Bogdanov and we, what they call is, the result they proved is that if the circuit size is C, circuit size is S, and the bound on the degree of the polynomial is D, then and randomized poly SD we can test. This is very simple proof of this theorem. So what really you have to do is that it's basically 2-line proof. So what you do to get such a result, that substitute your Zi by an indeterminate matrices of, let's say, roughly like d by 2 cross d by 2, and let's call this matrices, let's call it k cross k, where k you think of like d by 2 so for every variable you give a different set of matrices. Then the polynomial, let's call this matrices Mi. Then the polynomial will be simply this. And what does Amitsur-Lebesky theorem says is that this matrix that you finally get, whose entries are itself polynomial, it cannot be a zero matrix because it's not a PI for such a ring. So in particular, this is like a non-zero matrix. And once you know that it's a non-zero matrix, in fact some entry is non-zero, then you just plug random values to get a non-zero scalar entry in that particular position. So let's call this matrix as MF. So I know that MF is not a zero matrix, so there will be some entry somewhere, and this entry of this matrix is just a polynomial. It will be some polynomial over these y variables, which is non-zero, and the degree of the polynomial will be of course bounded by the original polynomial of the original degree of the polynomial. Then you just using Schwarzschild make random substitution at this point and get a non-zero. That's the idea. Now notice one thing is that if you are given a circuit C, the degree that the circuit can compute could be exponential in the size of the circuit. So this is efficient only if you put this additional restriction that the degree that the circuit generate, this is bounded by some polynomial. In particular, if it something like 2 power s, this algorithm is exponential time algorithm because the dimension of the matrices will be itself exponential. Is it clear? The point is.
So a priori you know the dimension.
Yeah, let's say these parameters are given. The size of the circuit is S, and the maximum, the degree that the circuit computes, that the degree of the polynomial is bounded by D. And in general, the D could be like exponential in the size of the circuit. So it could be like 2 power s. But because of this additional promise that D is small, you can just substitute by suitable dimension of matrices and do this identity testing. So in particular, if you do not put that restriction, then this K could be something like 2 power s. Then you get a huge dimension matrix here. You want to say?
So why doesn't this also need a large field because you have to choose the values for the
That's the final you need, but as a statement of Amitsur-Lebesky, you do not need the large field.
No, but
For algorithmic purpose, finally you need a large field,
even in the Bogdanov
even in the Bogdanov V. That is because of the Schwarzschild lemma application, but as a statement of Amitsur-Lebesky, it holds for every field. Yeah. For that algorithm purpose, finally you need some big field. But as a theorem just over rings, you do not need big field. It holds for every field. Yeah. So now let's look at what the new theorem offers. So now your D could go to like 2 power s, the size of the exponential in the size of the circuit, and let the number of monomial is let's say it is also like single exponential in the size of the circuit. Then the dimension of that algebra that you have to substitute, it's something like s plus 1, which is still small in the only in the polynomial size of the circuit. Then you basically do the same argument and get a randomized identity testing algorithm. But
Here the other question also is interesting. That what is the when I want to suppose it it is an identity, but for a large D, can you find, I give you a polynomial.
Mhm.
And suppose it is actually an identity, but say like the characteristic polynomial.
Mhm.
Of course, I know that if I plug in matrices of that size, then of course it is going to become 0. But I give you an arbitrary polynomial, and I tell you, is there a D? Can you find a D for which this becomes 0 when I substitute? Does this question make sense? Because even that seems to be interesting. Because you are saying when I put matrices of small size, it will not happen. But what if I use there?
But I mean, it will probably depend on your polynomial. I mean, like I mean, you cannot just say this question only for the number of variables and degree.
Is it?
I mean, different polynomial could be identity for different dimensional matrices. That's my impression of this question. So I think this question cannot be just phrased on two parameters n and d. You have to tell. I think if I understood correctly, Kevin's question is that given a polynomial, maybe like a black box, can you tell like which dimension of algebra it will vanish?
Is it 0 for some large enough?
Small, because large enough it can't be because of absolute.
No, I mean, his degree also like a parameter, like
When the matrix algebra gets larger, it becomes harder to be 0, right?
yeah. So I mean, of course, the dimension of the algebra should be inside the dimension provided by Amirsud-Levesky theorem. But if you want to know the exact dimension on which that, then I don't know that such a thing can be answered very neatly. But here you are interested in the other side of the question, like to test whether it's identity or not.
Kevin's question is at least as hard as PID, right? Because if I give you a commutative circuit and ask you, does it vanish over dimension 1 algebra? That is exactly PID.
Also, the regime where I'm working, it's all like randomized algorithm. So, I mean, in randomization, you can answer many things. Yeah. So notice one thing is that if you take a non-commutative circuit C of size S, the polynomial that the circuit computes can have actually double exponential number of monomials. So, for example, take the simple polynomial x plus y power 2 power s. This polynomial has a circuit of size roughly s. It's just repeated multiplication or like powering, but the number of monomial that the polynomial will generate it like 2 power 2 power s. So, in particular, this theorem gives you efficient solution only when the sparsity of the polynomial is a single exponential in the circuit side. It doesn't solve completely the problem. And because coming back to Srikant's point, you cannot improve this bound too much because of this polynomial S2nx, which is called usually standard polynomial. This is an identity for M and F. And if you look at the number of monomials that this polynomial has, you can understand that this theorem cannot be improved much. It's nearly tight. Yeah. So the main advantage of the theorem is that it gives you a different parameter sparsity into account, but as far as algorithm is concerned, is of course randomized. You cannot hope to de-randomize it, because even for the small degree, we do not know how to de-randomize such an algorithm. Okay, so this is the background that I wanted to tell you. So let me give you some sketch of the proof, how the proof goes. So, okay, so let me start with the first step of the proof, which is not really necessary, but it's nice to do it. So that's called a bivariate substitution. It just looks nicer to do it in the bivariate setting because that automata that we will finally use, that we are usually happy to work over two alphabet automata, 0 and 1. So, yeah. So this is your polynomial. And make a bivariate substitution, that is substituting zi by this x0, x1 power I. It's just an encoding. So every variable zi you just write like over new variables x0, x1 power I and x0. So this will change every monomial of the polynomial f into the monomials over the new variables x0 and x1. Let me call that polynomial also by, without introducing other notation, just that polynomial also I call f of x0 and x1. So it is clear that this polynomial is identically 0 if and only if this bivariate polynomial is also identically 0. Why? It's simply bijection between the monomials of the original polynomial and the monomials over this encoding. It's very simple. Now look at what is the degree of the new polynomial. If the degree of the old polynomial is d, every variable you have replaced by something like at most n plus 2 length string. So the degree of the new polynomial will be at most like n plus 2 times d. That's the reason that parameter n plus 2 times d enters into the theorem statement. Okay, good. But this step is not necessary. You can do it without this bivariate substitution also. It just looks nicer. So now one really interesting thing about this non-commutative computation is that you can view this monomial just like an words over an alphabet, rather viewing them like a truly algebraic object. That buys you a lot if you think them just like them as a word. So for example, now our polynomial becomes CIWI, where CI's are field element and WI's are words over, let's say, x0 and x1, and degree of f, let's call it d, which is at most we know it is n plus 2. So you are in this situation now. Okay, good. Now, if you look at almost any PIT algorithm, even in the commutative setting, every algorithm does something very similar. Somehow they try to isolate one monomial of the polynomial from the rest by putting some weight or doing some very clever thing, and that step is called isolation in almost every PIT algorithm. So here also we do a strategy similar to that, but in the non-commutative setting. So let me just, it's really simple. Let me just try to explain that. Let M be a collection of words over x0 and x1 of length, let's say d. So typically a word will look like xb1, xb2, xb3 and xbt. What are these things? These are xbi's are either x0 or x1. Their length is d. Now if you take a subset I of these indexes 1 to d, you can define like let I equal to, let's say I1, I2, Ik. These are just some positions between 1 to d. You can define the projection of the word w restricted to I very naturally. You just pick up those locations indexed by the set I. So, it is simply x b I1, x b I2, very simple. Now, let me give a little bit of definition. Let us call a set I is isolating for the set M, which is like set of strings, if there exists a monomial or word inside the set such that w restricted to I is different from for any other w. Let us call such a w, let us call it isolated monomial. What I am writing is very simple. Let us say the scripted M is a set of words of length let us say d, and I want to call like a set I which is subset of 1 to d is isolating if there exists one monomial or one word in the set, so that when you project in that location indexed by I, that monomial looks different than any other monomial in the set. Call that set I is isolating and call such a monomial is like isolated monomial in that set. So, that monomial is distinct with respect to that set I than any other monomial. Now, if I give you a collection of words, what is your guess that what could be a length of an isolating set or size of an isolating set I? So, it is very easy to prove that there exists an isolating set I of size